Alright, guys, good morning. Welcome to another series. In this series, we'll be talking about simple shell, and for this simple shell project, I'll be breaking down the things we know into phases. Now, in the very first phase, we'll be talking about processes and arguments. Now, under processes, we'll be talking on what are types of process, parent and the child. Talking about getting the process ID of a running program. Then we'll also talk about arguments to main, using void arguments, getting strings, input with functions, also doing string splitting. Now in the phase 2, we're dealing basically with system calls, what are system and library calls, forking, what's the fork system call, the orphan and the zombie again. Then we'll look at loading a program to a process using the exec v. Then you also know how to use the sleep and wait. Then we'll make a running instance till EOF, that means an end of file transmitter, which is basically the control D. That's when you're pressing your control D signal. We're also looking at getting file info from a file using the stats command. And well, I hope we have the time and to also get down to finish all this taxes here. So with that said, let's quickly get into the main topic. Now today we'll be looking at process. Now what are process? Well, to just be plain and to just be explicit without adding too much technical grammar to it, process simply means a running program. That's just this. A process is what? A running program. As it is now, I am running a process. And what's the process? I am on my Google Chrome, because Google Chrome is still running. I haven't terminated it here by closing it. So it's a process. Remember, a process is a running program. You get. Now, as you can see, my vagrant here, so it's a process because it's still running. A process is a running program. That's what we should just have at the back of our mind. It's very, very easy for us to understand it that way. Let's cut out all the technical terms. A process is a running program. To some, they might say, okay, it's a running instance, or better, they can say it's an instance of a program. Now, every process, so that it won't be conflicted, because as it stays now, this is my vagrant. I can also open another vagrant terminal here. You could see now I can still SSH still to this same machine, and yet there will be different sessions. There are different sessions. So to not conflict processes with each other, there's what they call process ID. Now every process that is being initiated or that it is being spawned has this process ID. It is the identification number that is automatically and randomly generated to every process that you run. So when I run this here, the process ID is different from the process ID that is currently running this guy here. Don't worry, we're seeing a practical explanation, demonstration. You guys, you know me that I like doing things practical, so we see it. So when a process is being created, it automatically generates, the system kernel generates the ID to match it, so it could actually trace it. Now there's also what they call a process table. Don't worry, we'll get to see this gradually. Now, since we understand what is process and what is process ID, I think I could just write it. What are process and okay. Now there are types of process. At least to some, they can say the forms of process, but I'm going to call it types because there's also a parent and a child process, which I would like to call forms. Okay, so now there are types of process. Well, you have the init process, the daemon process, zombie, orphan process, and user. I call them user defined because you're the one that's created the process. Like me, kind of opening my Chrome or probably my Adobe or my PowerPoint. I'm the one that created those ones. I have control over them. Now the init process, it's the mother of all process. It's the first process that it's been spawned once your kernel loads up. Like when you you can have a Windows kernel or a Linux kernel. Kernel is more like an architecture that manages your hardware. So when you power in your computer system now and your kernel starts, your kernel then calls this init process. To be very very exact, it's actually your kernel actually calls the system D process, and the system D actually has two tags there. The system D then start loading all your file system, building all your dependencies, and then calls the init process. So you could see that from your kernel you have the init processes. Now I'm going to go to daemon process. So what I want to just let us understand is that the init process is usually the first process, the mother of all process, which has a process ID of 1. Now what are daemon process? Well, daemon process, these are background process that we did not start them. They just run, and they run for the purpose of communicating with services. Yes, communicating with services. Probably you are doing networking, or basically it is networking. I did, to the best of my knowledge, like your SSHD, your FTPD, your HTTPD, your NTPD, network time protocol. You get, so these are processes that are running in the background, and they are usually for networking, communicating with networking services. You get, so those are those. But then you can actually, though we are not the one that started those processes, but then you could actually manage those processes. There's a way you could manage all your daemon process, because it's still not too nice to have a bunch of daemon processes running. So that's that about init and daemon processes. Now what about our zombie process? Now what is a zombie process? Now a zombie process is a process that has not been removed, or we could say in technical term ripped. By ripped, this is what I mean. By ripped, I mean this, not this. That has not been ripped in caps. This ripped in caps, that has not been ripped out of the process table. Now quickly, now if I'm going to run a PS here and do in this, you could see now this is my process table. Now these are all the process now that are running. Majority of them, I am not the one that started it. Now you could see the very first one here, you could see is what you could see here is what the process ID of one, which is what you guys could see here is what is the init process. Now in the init here, I've actually forgot to tell you now to identify daemon processes. They are always preceded with the D. Like when I said the SSHD, your HTTPD, your NTPD, your FTPD, so all daemon processes are always ending with what D. That's where you could actually identify them. Now you can see this now, the key thread D. So this is a daemon process, which is having a process ID of 2. You could see the init process spawned this. By spawning, it forked out. Don't worry, we get to understand forking and all those stuff. But then it forked out all these processes, and you can see KSMD. Majority of them I'm not the one that started it, but then it loads up when I spawned this my virtual machine up. and then they go on. These are all my current working process, and then this particular one is being identified clearly that it's a daemon process with having a process ID of 666. Now you could see the command that started it. You could see the command that actually started it here from the user as being atd. I think let me just try and expand this a little bit. Okay, I think this is much more better. And then you continue. Now this guy here, it's my current shell process now, which is what, 1828. This is my current shell process. Now I could verify that by actually doing what, echo $, and you could see is what, 1828. So now the process that is actually waiting to accept my command is actually having the process ID of what, 1828. And what program is running on the process ID 1828? It's what, the bash program, because it's the bash shell I'm running on now. So when a process is not removed from this process table, that's what we call zombie process. Now how do you create a zombie process? Well, the rule is a parent actually rips, that's what they call ripping or remove. When you remove a process, it's called ripping a process. Now the custom is it's a parent that rips off the child. So now let's assume that's why I said we'll be doing this, because basically as their system calls, so we'll be doing that under our system calls, orphan and zombie process. But I want to take the time to just explain it now. So let me quickly go back here. Now when you create a process, now let's say I start a process and then a process gave birth to another process, meaning I then have I then have a parent and a child process. So let me quickly go and explain the parent and child process so we could actually understand this zombie. Now a parent process is the one that is being started. Now when a program starts and then it creates a sub process, that sub process is called what, a child process. So with this short explanation, we could see that the init process is actually the mother of all process, because we can even see it practically from our PS table here. Okay, well, me passing the PS, this is just going to give me a snapshot of my current this that I run, but putting the PS and this flag here gives me all. Okay, just wanted to just give us that. So if I want to see all my process that I could use the PS out, but then if I just want to see the snapshot of the user current shell, you could see I could just do this, and you can see I'm running on bash, which is 1828, and then the PS command, the process that was forked from 1828 to run the PS command was what, 1973. If you also look closely now, the next process was what, 1974, which ran what, the PS aux. Because now when this PS command on which a process ID of 1973 was created, it became a child process of the process ID 1828. Now as of that point in time, when it was still running in that short amount of time, it was still on the process table. Now this PS AUX is still run, it has run and it's done running. You can see the process ID of 1974. Now quickly let me go back here and let's just get the gist. Now when this PS was still running, this ID was still in the process table. Now when it was done running, it was 1828 that actually removed it from this process table. That's why you didn't see it. And when I run this PS AUX command again, it was giving a process ID of what, 1974. Now that we didn't see 1973, because 1828 actually removed it. By removing it, called what, is ripped it out of the process table. Now when the parent now doesn't remove this process from the process table and the child process is done running, it then creates what they call a zombie process. Remember, a zombie process is created when a child process it's not being ripped from the process table, becomes a zombie. Now let's quickly touch on orphan process. Now what do we mean by orphan process? Well, just like how zombie process is, orphan process is kind of different. Now an orphan process is a process in which the parent process is done running but the child process is not done. Meaning my parent is running, like let's assume 1828 is done running but 1973 is not done, like it didn't exit. Now how will you know it's going to exit? Because all child process, after once it's done running, it's going to return an exit signal to the parent process, and that's how. And all parent process actually have the process ID of their child. You get. We'll be dealing very very well. We'll be dwelling very very well on this concept here in system calls, but I just want to explain the gist about what is going on in this context here. So an orphan process is created when the parent is done running but the child process is still running. Now remember, the parent ought to rip the child off, right? Now when the parent is done running and the child is still running, you have created an orphan process. But then once that child is done running, it is still going to be removed from the process table. But then how is it going to remove it from the orphan from the process table? The init process adopts it. Immediately the parent process is done running and exits, and the child process is still running, and then the child process, immediately the parent is done running and exits and the child process is still running, immediately the init process adopts that child process. So when that child process is done running, the child process then sends its exit signal to the init process, and then it is the init process that now removes this child process from the process table. But it's different from the zombie process. It's different from the zombie process. Okay, all right, we've talked on parents and child process. Now how do we get the process ID of a running program? Well, using C. Now in the link this, I could just do a px and this, and then I could actually get this, or you could also do the top command and you could also see all. Now you could see SSHD, you could see system D that I talked about. You could see system D that I talked about having a process ID of 1. Then you could see SSHD having, you could see this again having a process ID of 2. That's K3D. You see SSHD to having a process ID of 1979. Yeah, I think it was 1979. Yes, 1779. Now this top command, it's still running because I have not pressed exit, so it's still running. Top command, this top process now is still running. I'm going to press in Q now. It has ended that process. Okay, now I could actually do this and get the process ID, but what if I want to do that in C? Well, there's actually a command called get PID. I have to press man get PID. Now what does this do? It says it returns the process ID of the calling process. Let's know that it returns the process ID of the calling process. Now for us to use this get PID or the get PPID, which stands for get parent process ID, this get PID stands for get process ID. Now we have to include this, the sys types.h, the unit td.h, and this two processes actually what does not accept any argument. That's why you are seeing what void here, and then it's going to return a p_t data type. But to be very honest, this function is actually going to return an integer, an unsigned integer, because you could see earlier that these are all positive integers, so we could actually use an integer to receive it. So let me just write a program and see, and let's just call this, let me say hash include. First things first, I'm going to hash include my stdio.h. then I'm also going to include my sys types, the type.h. then I'll still need to include my unit std.h. Alright, now I'm not going to return, so I'm just going to say void main void. Now I'm just going to say printf. I'm just going to call them directly in my printf function, and just say current process. It is going to be an integer. Then I'm going to say parent process. It's also going to be an integer also. Then you just come in here and say get speed for to be the current process, doesn't accept any argument, gets pped. Going to run this, and yes, and I'm done with that. Then I could actually just gcc, should I use the flags? Oh, let's just use the flag gcc wall, that's where instead, where extra tick. Then let's use a to be, oh no, let's use p to be our output file name. Oh, sorry about that. Okay, well, where extra, void main. Oh, okay, fine, that's a where flag, always checking for that has to be int main. But then if I do this gcc, this is a p.c 0 p without putting that particular flag there, see it's going to compile properly. But let's just keep everything good. So let me just change it to int. And then I have to put in the return 0 to just keep everything clean and orderly. So now, first things first, if I'm going to do the get pped, it's going to return this process id 1828, because it was this process that is actually going to spawn out this process now that I want to start. Now this process now that I want to start is a child process. It's what this man gets speed is talking about here. Is what this man gets speed is talking about. It's going to return the process ID of the calling process, is of what the calling process, because if I do this now to run this, it's going to create a process. Now this process is the one that is what calling the get speed function. So it's the get speed function is just going to return that process ID. However, if I run the get pped, it's now going to get what the process that gave birth to that process that is running or that is calling it. So let's see this. Now you can see the current process is what 2033, which is what a random number. but now my parent process is still what 1828 as this, because this is process now, which is what bash. Remember, let's go back to our ps. Let me just do a ps and then let's just see it. Remember, 1828 here is what my what bash, and you can see that this process id is randomly generated. Here is 2033. You can see here is 2035. I could not guess it, okay, because I just ran this now to be 2030. That means the next one will be 2024. I don't know, it's just randomly generated. At some point it might be orderly, at some point it might not be orderly. Okay, now what's the, I think we are done with this. Now what is the proxy kernel pidmax file? Well, yes, we've understood the fact that there are processes on our Linux machine or our machine. Every machine has processes. Now in the Linux, the proc syskernel, this pidmax is actually a file. It's a file. We could actually see it. Like if I do an ls then proc syskernel, oopsie, yeah, these are all the files. Then I could actually let me grab this to look for pidmax. Okay, listen, it ought to be here. Yeah, it's there. So why did grep not get it? Because this is the pidmax here. This is the pidmax file there. And I didn't call in grep. Because then, yeah, you could see it. Because I was then like, okay, what's this? I was kind of scared. Okay, so this file is a file we could actually open it up. Now this file is a file containing the maximum number of processes we could actually run concurrently. Now you could just cut it out. You could say the maximum number of processes I could run simultaneously is 4,194,304. That's the number of processes I could have running concurrently or simultaneously. Okay, now if I just basically want to just print this out, we could actually just write a bash script and let's just say print, let's just call it mxp8. Sorry, I'm feeling very lazy to type long. Let me use nano. Let me use nano to write that. Then I could just say my shebang bin bash, and then I could just say cut out from proc sys then kernel then _max. Yep, and then that's all. Oopsie. Yep, shebang bin bash cut out proxies kernel pidmax. Yes, I want to save that and enter. Then I have to change just going to add executable permission to this guy here so I could run it. Then I could run it by doing mx_pid, and then you could still see it, or I could still do it this way. You could see. So with that said, we've actually covered everything on this process. Now if you have any challenge still understanding it, you could actually reach out to me via my social handles or whatever, probably from my WhatsApp, or even in the comment section there. You could actually drop in your comments about your questions, and Looking forward to seeing you guys in the next video, where we'll be talking about arguments to a running program. I'll be explaining things we really need to understand on this part. With that said, I love you guys. Take care, stay blessed, continue your practice. Thank you. God bless you.